Another to solving involving chemical reaction. We might have a chemical, this one, that's a gas. Notice the gas phase of the hydrogen. Now, we can measure various conditions of that gas, such as pressure, volume, temperature, and we can calculate various other things from that process. So we're going to be combining the ideal gas law with the principles of stoichiometry, where we can relate the amount of one substance to another in a chemical reaction. Let's look at this first problem. 12.8 grams of aluminum reacts with hydrochloric acid. How many liters of hydrogen gas would be formed at 715 millimeters of mercury and 19 degrees Celsius? So we have an equation there, the same equation that I just wrote down. 12.8 grams of aluminum. 12.8 grams. So we have a mass of aluminum. The mass of aluminum is 12.8 grams. Now, it's reacting with apparently excess hydrochloric acid, and it's going to produce hydrogen gas, and we want to figure out the number of liters, or the volume of hydrogen gas that will be produced. So volume of hydrogen gas is unknown. Now, we are given the atmospheric pressure, the pressure at which the reaction is taking place. So the pressure is 715 millimeters of mercury, and we're given the temperature, 19 Celsius, and of course we have to convert temperature values to Kelvin. So we had 273, so we have 292 Kelvin. Now, the link in these problems is going to be the N value. N, the number of moles. So this is not known right now, the number of moles of the hydrogen, N of hydrogen. That's unknown, but we can figure it out using the number of grams, and can find moles of hydrogen. And once we have moles of hydrogen, we can plug it into our equation, PV equals nRT, and we'll have all of our variables to find the volume of hydrogen gas. So our first step here is, first we need to use stoichiometry, and we need to figure out the number of moles of hydrogen. So we'll start with our given value. We have 12.8 grams of aluminum. And I'm not going to go into the details of the process here. There are earlier videos that explain how to do this process. So we need to first convert to moles. So the grams to moles conversion is the molar mass for aluminum, 26.98. Let's round that to 27.0. 27.0 grams of aluminum in every 1 mole of aluminum. Then we need the mole ratio step. For every 2 moles of aluminum, we have 3 moles of hydrogen. So for 2 moles of aluminum, we have 3 moles of hydrogen. And that's what we wanted to get, right? That's the moles of hydrogen that we were trying to find. So we can stop there. We calculate the moles of hydrogen. Right, so this times this divided by this times this. You might want to write down the numbers on the top, the products first on the top first, the products on the bottom first, and then divide the two. And so that comes out to 0.711 moles of hydrogen. Okay, so this value here, 0.711 moles of hydrogen, that is N in the ideal gas law. So that's the N value for hydrogen. So now that we have the N value, we have everything we need for the ideal gas law. PV equals nRT. We have the volume as the unknown, pressure is given, N we just found, R is a constant, T is right there. Let's solve for the unknown, the volume. V then is nRT over P. And so we have for N, substitute the numbers, 711 moles. R, it depends on the pressure unit. Since we have this pressure unit, we'll want to use the value of 62.4 millimeters of mercury times liters over Kelvin moles. Since our pressure is already in millimeters of mercury, that's the most convenient value of R to use. The temperature is 292 Kelvin. And the pressure, 715 millimeters of mercury. All right, so we just calculate. Gives us 18.1. Cross out all the units, millimeters of mercury, Kelvin, moles, all of those cross out. And so our unit then is leftover liters, and we have found the volume of hydrogen gas that's produced from this reaction. Given 12.8 aluminum reacts completely. Let's try the next problem. Given this equation, if a tank contains 55.2 grams of butane, what volume in liters of oxygen is needed to burn all the butane at 0.850 atm and 25 degrees Celsius? So we need our equation showing how butane reacts. Okay, so we have 55.2 grams of butane in a tank. Butane is a gas, so we want to know what volume of oxygen would needed to burn all the butane at this pressure and temperature. So one of the big issues with burning fuels is trying to get efficiency. So using these pressure and temperature values, we can optimize the efficiency. So we have the grams of butane, and we'll need to figure out the volume in liters of oxygen needed to react with that. So we have the mass of butane, C4H10, and so that's 55.2 grams. We want to know the volume in liters of oxygen is the unknown. We have other conditions here. We have the pressure, 0.850 atm. We have the temperature, 25 degrees Celsius. And so once again, to solve this, we need to find moles N is unknown, but we can find it by using the grams of the butane to figure out the number of moles of oxygen, and then we can figure out the volume of oxygen. So it's a similar to the last problem. Let's not forget to convert our temperature values to Kelvin. So we have the starting value of 55.2 grams, and that's a butane. We need the molar mass to convert that to moles. So carbon is 12, hydrogen is 1.01. Solve times 4 plus 4.04, 52.04. So we have 52, let's just round that to 52.03 sig figs. So we have 52 grams of butane for every 1 mole of butane. And now it's the mole ratio. For every 2 moles of butane, we have 13 moles of oxygen. So for every 2 moles butane, 13 moles of oxygen. Solve for moles of oxygen. So we have 55.2 times 13 equals, divided by open parentheses, 52 times 2 close parentheses, gives us 6.9. 6.9 moles of oxygen. Let's check that answer. That sounds a little high. 55.2 times 13 divided by 2.0 times 2. Okay, so it is a bit high, but that is apparently the number of moles of oxygen that we need. So that's quite a lot for a gas. But if you look at the equation shows you need a lot of oxygen to react with the butane that's there. So now that we have the N value, we can use the ideal gas law, PV equals nRT, and we can solve for our unknown. So we're solving for the volume again. V is nRT over P. We can substitute or plug in the numbers. The volume is the number of moles, 6.9 moles, times the ideal gas constant. This time, since we have a unit of pressure in ATM, it would be most convenient to use this unit for the R value, 0.0821. ATM times liters over Kelvin mole. And the temperature, 298 Kelvin. All divided by the pressure, 0.850 ATM. So now we calculate. Gives us a volume of 197, round 99, excuse me, 199 rounded to 3 sig figs, and the unit left over after we cross everything out. ATMs cancel, moles cancel, Kelvin cancels, unit left is liters. So 199 liters. That is quite a large area, quite a large amount of space So you need quite a large volume of oxygen gas at that pressure to react with the 55.2 grams.